All right. Sorry. Yeah, so hopefully everyone had a good weekend. And yeah, so we're going to continue our lectures in 364. Today is the fifth lecture number 4 if we're counting from 0. And today we're getting ever closer to that white whale that is gradient descent, that is basically the core of machine learning algorithms everywhere. So today we're just gonna brush up on the matrix calculus a little bit more. We started it last week, but I can see some eyes glaze over. So I want to just bring it home in this lecture, just to make sure everyone has that down, because it will be important later on. And then we're going to revisit computation graphs. We're going to revisit how computation graphs interact with that matrix calculus. And then we are going to end on some complex computation graphs that we will use next time for gradient descent. Does that make sense to everyone? So let's, and of course, I forgot to hit next. Okay. One small note: the version of the slides that I put on the website are slightly older than what I have right now. It has basically the same content, but I just the front matter was worded weirdly, and I changed it at the last minute. So I'm going to update it after the course, but you should be able to follow along even so. Okay. So let's recap matrix calculus, and let's see if you guys learned a lot from last week, or if we knew what we need to go over, huh? So let's say we have a scalar that's one value, that's a single variable x, and a vector of functions, f1 through fn. What is df dx? And I'm both looking for what's the shape of df dx and what are the values inside df dx. Yes, please.
So the shape will just be
Okay. Yeah. So yeah, exactly on the money. So the derivative of f with respect to x would simply be a vector, where each element of the vector is one of the functions of f, differentiated with respect to x, right? All right. Nice little warm-up. A little harder. Given a vector x and a vector of functions, f1 through fn, what is df dx? What do you guys think? Yes, please. It's a Jacobian matrix? Yeah. So what does a Jacobian matrix look like?
derivative of fi with respect to xj. Which dimension?
Okay, so let's say we're going to go numerator format. Actually, this is going to be a whole thing to describe. So so the derivative of f with respect to x, and I don't know why I put that there. Let me change that. Of f with respect to x, there we go, is simply the derivative with the gradient of each of the functions, and then the gradient with the gradients of each of the functions, and then the gradient each of the functions differentiated with respect to x, and that should be capital X. I'll fix that later. Well, capital X right there. And so the derivative with respect to x for the whole thing, so taking the derivative of a single function with respect to a vector gives you a vector, right? So we start off with a vector of functions, and then we take the derivative of each of these functions with respect to a vector, which means that each of these elements gets turned into a vector. So when we start off with a m size vector, quickly turns into a m by n matrix, right? Where each of the elements of the matrix, the columns correspond to the elements of x that we are taking the derivative with respect to, and the rows correspond to the function that we are taking the derivative of. Does that make sense? And of course, as you correctly pointed out, this is what's known as the Jacobian. The Jacobian, which is simply the change of a vector of functions with respect to a vector of variables. Okay, good. Yeah, I think that's good. That's good. Good. All right, so let's go over an important one that I didn't explain well last time, but I'm going to explain better this time. Consider the matrix A. We have an actual matrix A of size n by n and a vector x of size n times 1. What is AX? I'm going to stop correcting this eventually, but for right now, what is the derivative of AX times, what is the derivative of AX with respect to X? So who remembers what this was before? And there's an important caveat here, a very important caveat, which is that A is not dependent on X itself. A is independent of X. So who remembers what the value of this is? Yes. Yeah, it's A. What's your name again? I'm going to, huh? Dominic? Yeah, okay. I knew that, but then I was scared. Okay. Yeah, so Dominic, good, it's A. But why is it A? So let's rewrite this a bit. Let's rewrite this a bit, and let's just consider the matrix A multiplied by the vector X is simply a vector that is, are the dimensions correct? Matrix A by n and a vector size n by 1. Okay. Okay, so the matrix A times X simply becomes a vector where each element of the vector is the column of the matrix multiplied by the vector, piecewise, summed up together. Okay? Step 1. So you have this, and you could rewrite this. You could rewrite this, another way to rewrite this as is that each element in this vector is the sum of, again, the column, or do I have that correct? Oh, sorry, the row, yes. Yep. The row of A, yes, the row of A times the vector x to j, the sum of all those elements. Okay? And so each element here would be simply equal to, another way to write this vector is simply as the summation as each element of this vector I is equal to the summation of A, the row of A, times the elements of the row of A, times the vector x, the elements of x. Okay? Does that make sense? Nothing special. You guys have done this 100 times before. You're multiplying a vector matrix and a vector together to get another vector, and all we're doing is being kind of coy with the language and just rewriting it in a form that's very general. Okay? So now we need to take the derivative of this whole thing. We need to basically take the derivative of this with respect to x. Okay? So taking the derivative of this vector with respect to x, what does that do? It turns a vector into a matrix, right? Because for each value in A of x, we need to take the derivative with respect to x1, and then we need to take the derivative with respect to x2, and then we need to take the derivative with respect to xn, right? And we need to do that for every single value in A of x. Okay, so again, we're just taking the partial derivative. We're taking the partial derivative. We're writing out the matrix, or we're multiplying the partial derivative by the vector a of x to get a matrix where, to get an m by n matrix where each of these values is the partial derivative for the corresponding value of the vector ax with the partial derivative in x itself. Okay? And again, we're doing numerator layout. So rows correspond to the elements of ax, and columns correspond to the actual the elements of the partial derivative we're taking it with respect to. Okay? So now, good. So now, when we look at this, okay, let's really get in its face. All right, when we're looking at this function here, the partial derivative with respect to x1 for j goes to 1 to n of a of 1j times x of j. Okay? So if j is, for instance, 2, if j is 2, then it would be a of 1, 2 times x of 2. The partial derivative of that with respect to x of 1 is what? If j is 2 or 3. What's the partial derivative of those values with respect to x of 1? 0, right? Because it's not a function of x of 1. It's effectively a constant. So we take the 0. So the only time this whole thing has any value is when j is equal to 1. And so when j is equal to 1, we see a of 1, 1 times x of 1. We take the partial derivative of that with respect to x of 1. And what do we get there? We get this whole expression simplifies to a of 1, 1. Okay? And same thing here. The derivative with respect to x2 for the summation from j1 to n of a1j xj, for instance, so if j is equal to 1, it becomes a of 1, 1 x times x of 1. That is not a function of x of 2, so that becomes 0. But when j is equal to 2, then we get a of 1, 2 times x of 2. We take that derivative with respect to x of 2, so what do we get? A of 1, 2. Okay? And we do the same thing over and over and over again, and we see finally that the resulting matrix is simply a of 1, 1, a of 1, 2, all the way to a of 1n, and the values of the rows will be a of 1, 1, a of 2, 1, all the way to a of m over 1, m1. And so this is effectively just matrix A. Right? So taking the derivative of this matrix times x with respect to x gives you that A again. Does that make sense? Good. I wanted to really emphasize that because also when I look online, most papers and texts, they give you this. And they're like, well, you know this. The resulting vector, it just becomes this. And therefore, it becomes A, which is absolutely true. It's absolutely true. But sometimes it does the soul good to sort of write things out and convince yourself with a little bit of tedium at what someone is saying is actually true. Okay? When you're learning something the first time, it's not a bad idea to just go through the tedious process. Okay? Good. Okay, so. Oh, and one other thing I wanted to point out is that this makes sense. So with matrix calculus, again, what we're trying to do with matrix calculus is we're trying to match matrix calculus with normal scalar calculus. Okay? All mathematics is a bunch of old men trying to make all logic rules sort of match each other. And so when we're doing that, so we have to come up with that intuition. So the intuition behind matrix calculus should be, well, if we have a scalar times a variable, and we take the derivative with respect to that variable, what should we get? We should get the scalar again, right? That's how it works if it was one element. So ideally, that's how it should work when something's a matrix, when something's a different object, right? That's not always the case, but that's the aim with all of mathematics, okay? Yeah, okay, good. All right, so a couple little minor ones. What is the derivative of a vector with respect to itself? So supposing the function f of x is equal to x, and we want to know what is df of x with respect to dx. What should that be? If the function is very simple. Yep, Dominic.
From the last slide, we're showing this is the identity matrix.
Yeah, exactly. Should just be an identity matrix. So we could do the tedious thing also, same way as before. We just, again, if we suppose, I don't know why I keep putting y there, but we just have a vector of functions. We take it with respect to a vector, or with respect to the x vector. We write it out. This becomes a matrix because we have to take this function with respect to an entire vector from x1 through xn. So again, we have to write it out. We expand it out from a vector to a matrix. And then after all of this, we actually insert in what the actual function is. So f of 1 is equal to x1, f of 2 is equal to x2, and so on and so on and so forth. And so what do we see when we get to this point? We see, well, the derivative of x1 with respect to x1, that's 1. The derivative of x1 with respect to x2, what is that? 0. And so on. So we see that basically the only time, the only parts of this matrix that have any value that isn't 0 are along the diagonal, where you have the derivative of a variable with respect to that same variable is equal to 1. And so you get the identity matrix, okay? And again, makes sense according to the rules of calculus, simply because if you take dx, if you take the derivative of x with respect to x, you should get 1. And in matrices, 1 is simply the identity matrix. Okay? Okay. Wow, that picture came out small. Oh, well, I'm going to make this bigger. There we go. There we go. There we go. So one other thing, as far as dimensions go, I wanted to emphasize this, is that as far as dimensions go, they follow intuitive patterns. So if you're taking basically the derivative of a function that's a scalar with respect to another scalar, you get what? You get a scalar. That's normal calculus. If you're taking the derivative of a function that's a vector with respect to a scalar, what do you get? Well, you get a vector again, right? Because you have a vector of functions, and you take each of those derivatives with respect to a single variable. That makes sense. And similarly, if you have a scalar, but you need to take the derivative with respect to a vector, what do you get? You get another vector, simply because you need to take the derivative of this function with respect to x1, then you need to take the derivative with respect to x2, then you need to take the derivative with respect to x3, et cetera, et cetera. And then if you have a function that's a vector, and if the thing you're taking the derivative with respect to is also a vector, then you would have a matrix, right? Because you have one function, f1, and then you would need a vector to take the derivative of f1 with respect to x1, x2, x3, x4. Then you need to do the same for f2. Take the derivative with respect to x1, x2, x3, x4, and so on and so forth, right? So when you do matrix calculus, this is a good thing to be aware of. Okay, just be aware of if the function you're taking the derivative to is a vector or scalar, and if the thing you're taking with the derivative with respect to is a scalar or vector also. And you're going to see instances of all of these. with most deep learning models. All of these will come up. So be aware of your dimensions. Okay. I think last lecture or the lecture before last, we had element-wise operations. So yeah, so given two vectors, w and x, we had this idea of a Hadamard product, which is simply the element multiplication of two objects. Basically, we have two matrices, and for every of the same dimensions, and for every element in those matrices, instead of doing the matrix multiplication, we do the element-wise multiplication, right? Hopefully, you guys remember that. So that's also just if you're in PyTorch, that's basically just the multiply symbol, right? That's a Hadamard product, okay? And also, I think it's torch.dot that does that, right? Anyway, so what's the back to the actual question, geez. So what's the Hadamard product? What's the derivative of the Hadamard product with respect to x? Hadamard product between w and x with respect to x. Yes, please.
So every element of the product is going to be wi times xi.
Yeah.
When you take that with respect to xi, you get wi. Otherwise, you get 0. So
Yeah.
you get a matrix where the elements of w are along diagonal.
Oh, that's a good. That's how. What's her name again?
Patrick.
Patrick. Yes. Yeah. Okay. That's the logic. So, what's the logic here? It's that for every one of these elements. Did I forget to put the indices of w? Yes, I did. Oops. Oh, well, actually, no, I didn't. Yeah. No, I didn't because it's outside the parentheses. Yeah. So what we have, the Hadamard products of wx is simply, w1 times x1, w2 times x2, w3 times x3, that sort of thing, right? And then we have to take the derivative with respect to x1, x2, x3, x4, xn, right? So we get a matrix there, right? Because w dot x is a vector, and then you have a vector, you're taking the partial derivative with respect to x, you're supposed to get a matrix out of it, right? So that much is clear. We have to end up with a matrix. So as Patrick pointed out, we have a slight issue in that, well, not an issue, but we have when w dot x is a product, when w times x, when we have w1 times x1, then we take the derivative with respect to x1. Then what's the derivative of this? This becomes simply w1, right? And if we have and if we have, but in the cases where we have w1 times x1, we take the partial derivative with respect to x2. What do we get? We get effectively, we get 0 here. So the off-diagonal components of this matrix become 0. The on-diagonal components become w1 times x1 with respect to x1. So that becomes w1. w1 times x2 with respect to x2. That becomes w2, and so on until we get to wn. So it should be, what should this be? This should be the identity matrix. Is there an error here? Yeah? What's the error? What should this be?
A w identity matrix?
Yeah. It should be just, well, yeah, it should just be identity matrix times w. Maybe I did that intentionally, and it wasn't at 3 a.m., and I was really tired. Who knows? But yeah, it should just be the identity matrix times w, okay? That makes sense? Okay, some interesting elements some interesting ones to consider. Sorry, some interesting element-wise. Yes. Just wanted to put in sort of a quick cheat sheet on interesting element-wise derivatives to consider. So this was the Hadamard products right here. And another way to write identity times W is just simply say diag W. That's sort of a mathematical notation. Yes, please.
I times W is a vector, not a matrix. So I times W is different.
Oh, yes, yeah. You are absolutely right. I times W is vector, yep. Yeah, you have to do diagonal. Yeah. Yep, yep. There we go. Oh, but then it's, no. Why did it go to the next? Whatever, it's not that big of a deal. Okay, I was like, it should be over there. Anyway, it's always something with LaTeX, with MathJax specifically. Anyway, thank you for that correction. Absolutely. So, yeah, that's I times W is a vector, not a matrix. So we have to have a special function diagonal times W. I always keep getting that one wrong. I don't know why. What was I saying? Wait, W times I is the diag, right? Yes, if I reverse it, that's correct, right? I always get the dimensions. So that, let's think about that. No, it's not. Okay. No, it's not. That's wrong. Yeah, I'm trying to think, is there a mathematical definition, other mathematical definition for this, but I'm pretty sure it was, but I'm not thinking of it right now. Anyway, this is fine. Diagonal W is fine. I don't know why I'm like becoming so pessimistic on it. I'm trying to avoid it. But anyway, so some useful element-wise identities anyway. So if you add two vectors together and then you take the partial derivative with respect to one of the vectors, what do you get? You get the you get the identity matrix. Why? It's because same reason that if you have a function that's basically x plus some constant and you take the derivative with respect to x, then you get 1, right? So same deal here. You add a constant to, you add some value to a vector, you take the derivative with respect to that vector, you get identity back. Same deal here, w minus x, you take the derivative with respect to x. What should happen? This w goes to 0, this x, this -1 comes through, so you get -1 times identity matrix, which makes sense. So we talked about that Hadamard products. It becomes diagonal w. And the derivative of w, we won't go through, I won't go through sort of the tedious writing out the whole matrix. But the derivative of the quotient, what should this happen? If x was just a normal variable, then it would be w times x to the -1. Then the derivative of that, you bring the -1 down. It would be negative w x to the -2, which is exactly what you see here, right? So same rules of calculus that you've been following before, apply here also. Make sense? Okay. And yeah, all of these functions come into play. I haven't seen quotient in a long time. I haven't seen division. Can't think of where division is, but most of these functions come into play. Okay. So taking the derivative with respect to functions with respect to functions that are targets of variables, it's largely the same. So for instance, and I didn't want to do this, I wanted x. So for instance, let's say y is the sum of two functions that are predicated on their own variables respectively, w and x. So we have y is some combination of some element-wise combination of f and g, what do we get in this case? Well, we get y is equal to f, some combination of g. I'm using this circle as just sort of a blank symbol. It could be plus, it could be multiply, it could be minus, any of those element-wise functions. So the Jacobian with respect to w would be pretty straightforward. It would be the combination of each of those functions with respect to w1, w2, wn, and for each of those functions in the vector. The Jacobian with respect to x would be the same thing, except simply f of w with respect, it's the same thing except with respect to x, with respect to x1, x2, x3, xn. And so if we do it out, if we simplify this a bit, let's say that we know f of 1. Oops. Let's say we could simplify this a bit, and let's say in this case we're going to say that f of 1 is only dependent on w1, and g of 1 is only dependent on x of 1. Okay? We're just saying the functions themselves, g, f, and g, are element-wise. In that case, then we have a case where all the off-diagonal components go to 0, all the on-diagonal components are some value f combination with g, and yeah, makes sense. Yeah, and like so. Okay, so the point of this slide is basically just to show you that the same sort of math that you did for the vectors themselves, it carries through with the functions themselves, okay? And we're going to go over the chain rule in a moment. Other important calculus functions. Oh yeah, so other important calculus identities. This one got messed up. Hold on. I don't know why the rendering is. Why is the rendering off? Okay, well, what can you do? So other important calculus identities, for instance, scalar expansion, as we went through, f of x, f times x with respect to x is equal to f. That makes sense, assuming under one condition. What's that condition? When is this true? Yeah, please.
F isn't reliant on x?
Yeah, it's when f is not itself, it doesn't use x. Or it does not, yeah, it basically doesn't use x. Okay? So this is a scalar expansion, for instance, if you want to multiply everything by 2, or if you want to multiply something by some function, right? You want to have some polynomial multiplication of the vector. This is where this comes in handy. Also, so vector sum is kind of interesting, simply from the standpoint that it's used very frequently. Okay, this looks slightly better. So an easy way to do this. So vector sum is when you're just trying to compress dimensions, as you do very frequently in many deep nets. So you want to turn a vector that's n values into a single scalar value. Okay. So taking the derivative with respect to x here would be simply that you have to take the derivative of y with respect to x1, then with respect to x2, then with respect to x3, x4. And so another way to write it out would simply be the derivative with respect to x1 of the sum of all the elements of x for every value. Then with respect to x2, I'll fix this later. With respect to x2, with respect to xn, etc. So what does this mean? So what happens here? Well, you have basically a function here that's x1 plus x2 plus x3 plus x4 plus x5. And then you take the derivative with respect to x1. What happens? x1, all those elements except x1 go to 0, and the derivative of x1 with respect to x1 goes to 1, right? So all the elements that aren't x1 here go to 0. Then you have to just take the derivative of x1 with respect to x1. Same thing here, x2, derivative of x2 with respect to x2, derivative of x3 with respect to x3, etc. So you get a vector of 1s. Okay? So I think that's interesting. That's going to come up. That'll come up in convolutional neural networks and maybe linear gradient descent also, depending on the network. So that's kind of a common one also, just to be aware of. So one of the reasons we're going through all of this is to basically beat this into your heads of like how matrix calculus works, and that for any given function, we could take the derivative of that. We could have the derivative of that function and sort of get a closed form expression for what the derivative of that function should be, right? So when relating this back to PyTorch, PyTorch literally for every single one of these functions, for every single one of these cases, like this, PyTorch has a YAML file that was pointed to in one of the previous lectures that literally has for every single function that you do on a tensor, then the backward pass, the derivative of that function, is some value, okay? Is some new function, okay? So that's what's machine learning, a big part of machine learning is, sort of getting the rules of the game set, okay? Trying to understand the calculus, trying to understand how functions multiply together, how they interact, how you could go from a variable to an input to an output, and also how you could go from the output to the input using gradients. Okay, make sense? Okay. I think I've beaten this horse dead. Does everyone understand matrix calculus? Right? All right. All right, so you all should be experts on linear algebra and matrix calculus. No problems whatsoever. And now it's time for your first exam. No? Okay. All right, fine. We could talk about other things. Any questions before I move on? No? Okay. So next one. Single variable chain rule. Let's review that because we haven't seen that in a couple lectures. And we're going to expand on it a little bit. So let's consider the network that we saw last lecture. And I'm going to make you a slightly bigger. I don't know. All right, that's fine. So we have this function that is the composite of multiple other functions. And basically, g of x is a function x squared plus 1. H of g, h of h is a function log. K is a function sine. And then you chain them all together. You take the function of, you take k of h of g of x. And you get the function of f of x is equal to the sine of the log of x squared plus 1. Yep, parentheses match. Sorry, looked a little weird for me. Okay, makes sense? So we have this composite function, and what do we want to do right now? We wanted to see how the input affects the output. That's really what we want. We want to know if we change the input a little bit, how much does it change the output? Right? That's the whole point of all of this that we've been doing. But one thing that was bothering me about this function from previous lectures is that g itself is a complex function. It's not like that normal single operator function. It's plus and it's power and all of that. So we should break that up. We should get more consistent with PyTorch and keep our sanity. So in this case, I'm simply making g equal to e plus 1, and I'm making e equal to x squared. So that the results, there we go. So that the results is So the results is, so g is still x squared plus 1, but we have this other little function in its place, so that, just makes things simpler. Basically now e is the power function and g is addition, okay? Before, g was like this amalgamation of all sorts of things. Now we just want to keep each function sort of a primitive operator, okay? So that's fine, right? I didn't do anything there, right? Everyone's with me? Yeah, so again, we take the derivative. We want to know how much changing x a little bit will change the output y or f. Yeah, sure. We want to know how much changing the input a little bit will change the output. So what do? We take the derivative. We want to know df dx. And how can we solve this in this case? Well, f is simply equal to k. So we say we could chain these derivatives together to say we still first want to know the derivative of k with respect to x, the derivative of k with respect to h, and then times the derivative of h with respect to g, times the derivative of g with respect to e, times the derivative of e with respect to x. Okay? Make sense? So what do we do here? Well, k is simply sine h. So the derivative of k with respect to h is simply cosine of h. Then we'll keep that in our back pocket before we move on. And then we want the derivative of, okay, let's expand it out to the fullest. So we want the derivative of k with respect to h. So the k is sine h. So we know that the derivative of k with respect to h is cosine of h. Then we know h is simply what? H is equal to log x squared plus 1. So we substitute that in. So we get the derivative of k with respect to h is cosine of log of x squared plus 1. Right? That all makes sense. Then we multiply that with the derivative of h with respect to g. So what is the derivative of h with respect to g? H is simply log of g. So the derivative of the log function is 1 over that. And so the derivative of h with respect to g becomes 1 over g of x. And g of x, as we know, as we have beaten, as I've said exhaustively, is x squared. So the derivative of h with respect to g is 1 over x squared. Right? And so then we take the derivative of g with respect to e. So what is the derivative of g with respect to e? It's simply the derivative of e plus 1. So the derivative of e plus 1 becomes 1. So since no e is in there, we don't need to add in e at all. So the derivative of g with respect to e is simply equal to 1. And then we take the derivative of e with respect to x. What is that? The derivative of e with respect to x is simply 2x. So in this case, we just add in 2x. And so the derivative of f with respect to x is 2x cosine of log of x squared plus 1 over x squared plus 1. Make sense? That seems reasonable. Then we could evaluate this. It's always a good thing to doubly check your work with the computer, both have a theoretical understanding and make sure your theory is correct. So assuming x is equal to 1, we could simply evaluate this derivative as 0.7692. Remember, computers don't think in terms of symbolic notation. PyTorch is simply taking a small interval of a function and evaluating the derivative that way. It's simply taking the slope of a smaller interval of a function and be like, the derivative of f with respect to x is whatever this measurement is, right? So we have to always do this. We have to assume a particular value for x, and then we have to evaluate the derivative of that point if we want to match it with PyTorch, okay? So in this case, we could we could do the same thing. We could simply, remember, declare x to be a tensor, tell x to require the gradients, and simply put x through the through the operations that we did so before. And then we have our manual calculation. Remember this torch.nograd, what does it do? It basically tells PyTorch, don't include this in your computation graph. This isn't part of the computation of x. Okay. I don't think it's needed in this instance, but it's good to put it there. Anyway, so we take the gradients with respect to x. We say k backward. K backward just calculates the gradients of basically calculates the gradients of all the functions, and so the gradients of k with respect to x becomes 0.7692, which is what we had calculated manually, right? Makes sense, right? Okay, good. So, I don't know what happened. Okay, oh, it was calculating again. Okay, so, makes sense. So let's do this again. Let's do more examples. Why not? Let's change the example, though, a little bit. And instead of saying g is equal to e plus 1, I'm going to make g equal to x. Why not? Right? G equal to e plus x. Sorry. G is now equal to e plus x. And so the new function, f of x, is equal to sine of log of x squared plus x. All right. Should be doable. We could do the same thing that we did before. We have a particular gradients. We need to calculate the gradients, but we run into a slight bit of an issue, right? If we take a look, if we have this, if we want to calculate df dx again, what we need to know is dg de, right? But dg de, we have multiple options, right? dg de, we have, dg de is both comprised of multiple variables now. It's comprised of e and x. So, I mean, we have to do something with partial derivatives now, which sort of sucks. Not as simple, but we could either take the partial derivative with respect to e. That way we get the partial derivative with respect to e of g of d ex is equal to 1. Okay. Or the partial derivative, or we could take the partial derivative with respect to x. And we get 1 again. So it seems to be consistent, although weird, although it's unusual. But whatever. Us being good engineers, we're not scientists, we're engineers. And as engineers, we don't necessarily care if one thing is correct or not, as long as it works, right? So we're just gonna plow right through. We could go through and ask our physics professors what's going on and what we should do, or we could just plow right through. We could try a whole bunch of crap and hope that something works and just move on with our lives. Learn a lesson that way, right? So let's do that. Now, if we want to take df dx, we could take df dx and take dk dh times dh dg times dg de. Take the derivative of g with respect to e, and then times the derivative of e with respect to x. Get df dx that way, and so if we calculate df dx that way, we get the same function that we had previously. Basically, 2x cosine log x squared plus 1 over x squared plus 1. Or we could skip de dx altogether. We could simply take df dx, and then we can multiply that by dk dh times dh dg times dg dx. And we get df dx is equal to cosine log x squared plus 1 over x squared plus 1. Okay? So we got two different options for the gradient of f with respect to x. Well, whatever. Let's just go. Let's just see what PyTorch says. We have these two different options, and we just make x equal to 1 again. We'll just make x equal to 1 again. And so option 1, df dx is equal to 0.7692, exactly the same as what we had before. Option 2, df dx is equal to 0.3846, what we had before. And PyTorch will solve all of this for us, right? And PyTorch says if we do all of this, if we change g and then calculated the gradient again, we get 1.1539. So it turns out we're wrong. Turns out we're wrong. Huh. So what happened? Where did I go wrong? What am I not seeing? Please.
The
Down.
answer is just the sum of the two answers, so you probably have to do one way of doing the derivative and then add on the other way of doing the derivative.
That is true. Very, very astute, Dominic. Good math in your head skills. So it does look like, just looking at these options, it does look like the sum of the two options is equal to what PyTorch is saying. So clearly, we were supposed to combine these two options. But why? Why were we supposed to combine these two options? Well, the error is in what I did previously. The error here is simply that if I take the derivative with respect to x of g of ex, right? G of ex is equal to e times x. It's not equal to 1 because the derivative of e with respect to x is not equal to 0, right? E is a function of x, right? So because e is a function of x, we simply cannot exclude it and call it 0 and move on with our lives. We have to actually include it in our calculations. So what does that mean? Well, so we're literally getting a visualization. So the reason I didn't include the computation graph before is because it would have hinted to a problem. And the problem is e is a function of x, and g is a function of x. We have sort of fan out or fan in to deal with. So the question is, how do we deal with fan in when we're calculating these gradients? And the answer is really, really quite simple. We have the total derivative rule, which simply states that in order to compute dg dx, we need to sum up all possible contributions. So in this case, when we have a function that's two variables here, d of g, which is a function of e of x, we need to take the partial derivative with respect to x. That's normal. That's fine. But also, we need to take the derivative with respect to the other variable or variables, then take the derivative of those variables with respect to x. Did I change the sign of d?
Yeah, for the total derivative. We need to change the sign from the number d, sorry, to later d.
Say that again?
Left hand.
Oh, the left hand. What do I need to do here?
The total derivative, should we change the sign to the dg to dx, or just
What do you mean change the sign? Like make it negative?
I mean the reference sign,
The what sign?
derivative. Yeah, it's not
Oh, I see. Oh, so instead of using this, like basically making it. Instead of using partial, just say total derivative, d. I want to say, I think you are right. I think you are right. I will say that this is actually I've looked this up. This is actually sort of a contentious topic because mathematicians use partial and D pretty much interchangeably. But you are technically correct. Thank you. Yes, I'm pretty sure you're technically correct. Just when you're reading papers, don't depend on that. Trust me on that. So yeah, yes. Yeah, but you need to take the total derivative with respect to x. This is actually a good way to say it. Yeah, actually, I'm going to be more careful with this from now on. So in order to take the total derivative, you take the derivative with respect to x, but then also when you take the derivative with respect to x, when you have another variable, you should take the derivative with respect to that variable, then take the derivative of that variable with respect to x, right? So let's say that variable is independent. Let's say instead of e, this was y, right? This was y, and y is its own input, not dependent on x at all. Then you would simply put dg yx with respect to dy, then dy with respect to x. So this will be 0, and this would all disappear, right? So that's how it works out. We always do this implicitly. We always do this implicitly. We were doing this implicitly when we were doing matrix calculus. But the issue is that because we were doing it implicitly, it was something easy to overlook, right? So the point of a lecture is to make sure you guys see the things that are easy to overlook. And so the thing that we were overlooking is the total derivative rule, okay? So total derivative rule just means that in order to calculate the derivative with respect to a variable, you need to calculate all contributions from that variable into the derivative, not just the explicit contributions, but the implicit contributions as well. Make sense? So that's also why when we did the calculation via PyTorch appeared to be the sum of those two options, because literally, if we replace dg, dg, de, or dx with the sum of this, then this right here, this whole derivative of f with respect to x becomes the sum of both options, right? And so if we calculate out the entire derivative, we get df dx is equal to 1.1539, i.e. the sum of the other two options, which is consistent with PyTorch. So that's a pretty good hint that we're correct in that sense. Yeah? Okay, total derivative rule. All right, so total derivative rule gets us to computation graphs. So we're going to end on computation graphs today, but they are important. So we're going to sort of go to a complex computation graph, not the simple one that we saw before. I mean, we had fan in, we had fan in, fan out before. So really, the only difference now is that we're just getting more complex, right? So let's say we have a computation graph as follows. We have a computation graph that is the function of two variables, x and y. And each of those variables go through a bunch of different operations. Okay, so for instance, x goes through W1, and this value, and the value right here, W1 simply propagates the input. Okay, so W1 is simply sending the input x out here. So basically, this branch here becomes x, and this branch here becomes x. W2 does the same thing. And then W4, it's a multiply function, right? So basically, it takes in W1, the values of W1 and W2, and multiplies them together, and outputs a multiplication of them together. W2 or W3 is the power function. So what does the power function do? It simply takes in a value, or not even power, square function. So the W3 is a square function. It takes in a value and then outputs the square of that value. And then W5 is the cosine function. Takes in a value, outputs the cosine of that value. W6 is the multiplication function takes in two values, multiplies them together, and W7 is the increment function, takes in a value, outputs +1. Okay, so this is a computation graph which you guys have seen before. So if we follow the logic here, we could simply see that at the outputs we have basically x goes to xy here, cosine of xy times cosine of xy times x squared plus 1. Okay? By just following the graph incrementally. Okay? But this graph isn't really meant to be human readable. It is meant for actual computations. So for instance, if we want to calculate the forward pass, let's say the forward pass where x is equal to 2 and y is equal to pi over 2, then we could use it to calculate the actual value at f of xy, right? This isn't a what's the format for mathematical equations? Oh, operator tree format, right? With normal expressions, the way to depict that expression is hierarchy of operations, and so you get basically a tree that represents a mathematical formula, right? This isn't that. We're not representing a symbolic object. We're not a symbolic equation. We are representing here a computation, okay? The computer doesn't care about the symbols, what's x, what's y, what's z. Couldn't care less. It just wants to know, I have some inputs here. These are what's known as leaf nodes. You saw that when we looked at the computation graph using the torch utility. These are the leaf nodes. How do you go from the leaf nodes, which are a certain value, to the actual value at the output? So literally all you do, x is equal to 2, y is equal to pi over 2. We propagate it so that x goes to 2, 2. These branches become 2. And then at W4, we multiply pi over 2 with 2, and we get pi. Then at W, the output of W5 becomes the cosine of W4, which becomes the cosine of pi, which is -1. Right? Cosine of pi is -1. Same thing as the output of W3 is W1 squared. W1, it was 2, so the output of W3 becomes 4. W5, the output of W6 is simply the multiplication of 4 times -1, which becomes -4. And the output of W7 is simply equal to the output of W6 plus 1, which is -4 plus 1 becomes -3. F of x is equal to -3. Okay? So all you need to do is basically carry out the numbers from one operation to another. You have nodes which represent operations, and you have numbers which represent actual values. So what the computer does starts out at the leaf nodes, and literally all this process is called annealing. It sets the value at the leaf nodes, and then for every node that the leaf nodes are connected to, it starts calculating what is the output of that node. So it goes through that graph multiple times, and every time it marks the outputs of more and more nodes until it gets to the output nodes, the value of the output nodes, okay? So if you have ever dealt with graphing algorithms like shortest path, exactly the same idea. You're just going from some value, you're just going from leaf nodes to, from start nodes to end nodes, just following a computation, okay? In a efficient manner. Also, what's important is that this is a very efficient manner. As you guys can see, this is a linear time process. Okay. Does the forward pass make sense? Okay. So, yeah, we got time. Okay. So, backward pass. So the issue is now that we got to calculate the backward pass. Okay, how do we calculate the change in f given the change in y? Okay, and to do that, we simply consider the operations of the actual nodes. Okay, so the forward pass, so for W4, the forward pass, the output is here. For W4, the backward pass, it reverses its direction from the input and goes this way. Okay? So what is happening in this moment is that for every operations, as we said, Torch has basically a huge library of operations and their derivatives. And so at every node, we create a new edge. This will be a backward edge. And the actual function of that backward edge depends on the operation of this node. So for instance, W7 was the increment operation. It simply took in an input here and added 1 to it. Great. So what happens when, what's the derivative of W7 with respect to its input, W6? Well, it's the derivative of W6, it's the derivative of W6 plus 1 with respect to W6, which would be 1 here. Okay? W6 was the multiply operation, right? It multiplied 2 inputs together to get the multiplication of those 2. So what do we have to do? We have to create backward edges for each of its inputs and take the derivative of W6 with its first input, which is W3. So we take the derivative of W3 W5 times W5 with respect to W3, and what do we get? We get W5. Same thing here, is that we take the derivative of W6 with respect to W5, and what is that? Well, W6 is equal to W3 times W5, so the derivative would be W3. Okay? So all we're doing with the backward edge is that we're creating new edges that go from output to input, and the user doesn't define anything. The edges are defined by the functions by the operations of the particular node. Make sense? So we go through, for instance, W5 is the cosine function. It takes the cosine of its input. Now we want to go back. We want to send its input back. We want to take the derivative of W5 with respect to its input. So the derivative of cosine, which would be negative sine with its input, with respect to its input. And we do the same thing. W4 is simply the multiplication of 2 variables. So then we take them back. So we take the derivative with respect to each of those inputs. We get W1 and W2 respectively. And W1 simply propagates the inputs. So W1 is simply equal to x. We take the derivative of W1 with respect to x. We get 1. We take the derivative of W2 with respect to y. We get 1 there. Okay? But usually, we don't add those variables in simply because it's implicit that the first node here would always be propagation node. Okay? Make sense? So we could use this. Oh man, okay. I thought I formatted this differently. I was just working on this. Okay. So we could use this idea. We could use the chain rule again, right? To get the derivative of. So to get the derivative of a particular value with respect to any, we could use the chain rule to accumulate the gradients and get the derivative of any of a value with respect to anything else. So for instance, over here we want the derivative of WF with respect to W7. We go here, we look, and the derivative of WF with respect to W7 is 1. And we get the derivative, we could accumulate the gradients. So we get the derivative with respect to W6 is simply 1 times 1, 1 times 1, which is 1. And then we accumulate, we find our accumulation backwards to get 1 times 5 times, and if we have multiple edges coming into a node, we add them together. So 1 times 5 times W1. Oh, W1 is here. Oh, times 2 times W1, 2W1. Why, okay. W3, 1 times 1. One times 1 times 1. Let's see, this one, 1. I'm getting half the graph. Yeah. 1, W3, W3, yep, the W sign 4. Negative W2, yep. Yep, so negative W2, W3, that, yep. So W5. Oh, this is a squared. I'm looking at the reverse thing. Yep, 2W1, yep, there we go. Yep, so yeah, 1 times 5, then 2W1. So we get W1, the change in the gradients of df dx is equal to 2W1 W5 minus W2 W3 sine of W4. And then we could follow the paths in the other direction to y, simply going on the backward edges. 1, W3, negative W3 sine W4, negative W1, W3 sine W4. Okay? So all we're doing is the accumulation. Okay? And again, this is the symbolic expression. For the actual value, we would have to plug in the actual values that we get from the forward pass, right? Because now these values are just simply from the forward pass. So going to the next layer, there we go. This is formatted correctly. Going to the next layer, we get a total df dy of negative x3. Oh, yeah. We get a x is simply equal to, W1 is equal to x, so we substitute that out to get x here. W5 is equal to cosine of xy, so we substitute that out to get x here. And so subbing those values out, we get df dx is equal to 2x cosine of xy minus x squared y sine of xy. And then we could do the same thing. Df dy is equal to negative x cubed sine of xy. Okay? So this is a symbolic expression, but if we actually assign values, for instance, if we make x equal to negative 4, if we make y equal to pi over 3, we could calculate out the gradients without we could calculate the gradients out without with using torch and without using torch. And what we get, those gradients at the W1 and W2, which are equal to the gradients of x and y respectively. We get a manual calculation, which is equal to 0.0931, and a PyTorch calculation, which is equal to the same thing. Okay? So that is how you could use a computation graph to calculate the gradient of an output with respect to a particular input, without really knowing much about the function itself, right? In this case, the PyTorch knows nothing about the total function in the end. All PyTorch is doing is creating that computation graph and then creating the forward arrows. So the forward arrows are created here by the user, and the backward arrows are created by PyTorch automatically. And then when you actually need to calculate the gradients, you simply follow the backward arrows getting the numerical value and obtaining the actual gradient here, actual numerical value here for each input. Does that make sense? Okay, so we are going to go over this computation graph and more next time. And then that'll give us the ability to go into gradient descent and what gradient descent actually means. So thanks for coming today, and I'll see you on Thursday.